What is nuclear power? Nuclear power is a method of generating electricity using nuclear fission, a process where the nucleus of an atom is split, releasing a tremendous amount of heat. In nuclear fission, the nucleus of a heavy atom like uranium is split into two smaller nuclei. This process releases an enormous amount of energy in the form of heat. This heat is used to boil water, creating steam that spins a turbine connected to a generator, producing electricity. Nuclear power plants use uranium fuel rods arranged in assemblies. Inside the reactor, these fuel rods undergo controlled fission reactions. A nuclear power plant consists of several key components working together to convert nuclear energy into electricity safely and efficiently. Nuclear power is a low-carbon energy source that provides stable and reliable baseload power. It is extremely energy dense, and power plants can operate for many decades. A nuclear reactor consists of several key components that work together to harness energy from nuclear fission. We'll explore four essential components: fuel elements, moderator, control rods, and coolant. Fuel elements are the heart of the reactor. They contain uranium-235, which is processed into ceramic pellets and stacked in fuel rods. These rods are arranged in fuel assemblies where nuclear fission occurs. The moderator slows down fast neutrons released during fission, increasing the probability they'll cause more fission events. Common moderators include water, heavy water, and graphite. Control rods absorb neutrons, allowing operators to control the reaction rate. They're made of neutron-absorbing materials like boron or cadmium. By inserting or withdrawing control rods, operators can increase or decrease the power output. The coolant removes heat from the reactor core and transfers it to generate steam for electricity production. Water is the most common coolant, though some reactors use heavy water, liquid metals, or gas. These components work in harmony to create a controlled, efficient nuclear reaction. Fuel elements provide the energy source, the moderator facilitates the chain reaction, control rods maintain safety and regulate output, and the coolant transfers heat for electricity generation. Safety is paramount in nuclear power plant design and operation. Nuclear power plants employ a defense-in-depth approach with multiple independent safety barriers. These principles include multiple physical barriers, redundant safety systems that serve the same function, diverse protection mechanisms, and rigorous inspection regimes. Containment structures are robust, multi-layered barriers designed to prevent the release of radioactive materials. The reactor core is housed within multiple protective layers. These include the steel reactor vessel, a primary steel containment structure, and a reinforced concrete secondary containment. These barriers are designed to withstand extreme events, including earthquakes, floods, and even aircraft impacts. Nuclear power plants incorporate redundant safety systems, meaning multiple backups for every critical function. These redundancies include multiple backup power sources, several independent cooling systems, automatic emergency shutdown mechanisms called SCRAM systems, and duplicated monitoring instruments. If one system fails, backup systems automatically take over, ensuring continuous safety functions. Modern nuclear plants increasingly rely on passive safety systems that function without external power or operator actions. These systems rely on natural forces like gravity, natural circulation, and pressure differences to cool the reactor. They continue functioning even during a complete station blackout and don't require pumps, fans, or other active components. For example, Westinghouse's AP1000 design can safely cool the reactor core for more than 72 hours without any operator action or external power sources. Nuclear power plants are subject to strict regulatory oversight from independent national authorities. Agencies like the Nuclear Regulatory Commission in the United States conduct regular inspections, enforce stringent licensing requirements, and require continuous safety improvements. The International Atomic Energy Agency provides additional international oversight. These comprehensive safety measures have made nuclear power among the safest forms of electricity generation. Nuclear power has the lowest fatality rate per energy unit produced when compared to other major energy sources. The industry has continuously improved safety measures since past incidents, and new advanced reactor designs incorporate enhanced inherent safety features. Through multiple layers of protection, redundant systems, passive safety features, and strict regulatory oversight, modern nuclear power plants are designed to operate safely under a wide range of conditions. Small modular reactors, or SMRs, represent a new generation of nuclear technology that is gaining traction worldwide. SMRs come in various sizes, from microreactors generating just a few megawatts to small reactors producing up to 300 megawatts of electricity. This is significantly smaller than conventional reactors that typically exceed 1,000 megawatts. SMRs offer several advantages over traditional reactors. They can be manufactured in factories, reducing costs. Their smaller footprint allows more flexible siting options. They incorporate enhanced passive safety features, and they enable scalable deployment where additional modules can be added as energy demand grows. NuScale Power has developed the first SMR design approved by the U.S. Nuclear Regulatory Commission. Their power module uses natural circulation for cooling, eliminating the need for pumps and increasing safety. A commercial project using NuScale's technology is planned to be operational by 2029. While many countries are developing SMR designs, China and Russia are currently leading in actual deployments. China is constructing multiple SMR projects, and Russia has deployed floating nuclear power plants using SMR technology. The United States, Canada, and the United Kingdom are advancing designs with commercial deployment expected in the coming decade. SMRs offer unique advantages in terms of construction and transportation. The modules can be fully built in factories and then transported to the installation site by road, rail, or water. This factory-based production approach significantly reduces construction time and improves quality control compared to traditional on-site nuclear plant construction. SMRs incorporate several technical innovations. Many designs feature an integrated approach where all primary components are housed within a single vessel. Passive safety systems that require no external power or operator intervention in emergency situations are a hallmark of SMR designs. Additionally, many SMRs are designed to be installed underground, providing additional protection from external threats. Looking at the deployment timeline for SMRs, many designs received approval in the last few years. Construction of the first commercial SMRs is expected to begin by 2025, with initial deployments around 2027. NuScale's first commercial project is planned to be operational by 2029, and widespread deployment of SMRs is anticipated in the 2030s as the technology proves its economic and safety benefits. Small modular reactors will play a critical role in the future of nuclear energy, offering a flexible, safer, and potentially more cost-effective approach to nuclear power generation. The next challenge to address is how to manage nuclear waste from these and other nuclear facilities. Several countries around the world are revising their nuclear policies to support the growth of nuclear energy. This global shift reflects a growing recognition of nuclear power's role in achieving emissions reduction targets. South Korea has scrapped its nuclear phase-out plans, now targeting 30% electricity from nuclear by 2030. Japan is recommitting to nuclear energy, aiming for 20 to 22% of its electricity generation from nuclear by the same year. The United Kingdom has committed to tripling its nuclear capacity by 2050, while the United States is showing unprecedented bipartisan support through new legislation. In the United States, the Inflation Reduction Act of 2022 represents a major policy shift, providing substantial investment and tax incentives for both existing and new nuclear plants. Historically, nuclear power has received disproportionately low tax incentives compared to its energy contribution. In 2017, nuclear produced 8.4% of U.S. energy, but received only 1.7% of tax incentives. Government support for nuclear power reflects the growing recognition of its critical role in achieving net zero emissions targets by 2050. Nuclear energy is essential for meeting climate goals as it complements renewable energy sources and provides reliable, carbon free baseload power that can operate regardless of weather conditions. Recent developments include an $840 million U.S. nuclear contract with Constellation Energy in early 2025 and a commitment from 22 countries at COP28 to triple global nuclear capacity by 2050. The private sector is also increasingly involved, with tech giants like Microsoft, Amazon, Google, and others investing in nuclear energy to power their data centers and AI operations. Nuclear power faces several major challenges, but also offers significant opportunities. On the challenges side, nuclear power struggles with high initial costs, regulatory complexity, long construction times, public concerns, and waste management issues. A single traditional nuclear reactor can cost between $5 and $10 billion, making financing difficult, especially with construction timelines that can stretch beyond a decade. Regulatory frameworks vary widely across countries and continue to evolve, creating a complex landscape for project approvals and licensing. Public perception has been heavily influenced by accidents like Fukushima and Chernobyl, leading to strong opposition in many communities, as shown in these protests. Safe long-term storage of nuclear waste also remains a significant challenge, requiring specialized deep geological repositories. Despite these challenges, nuclear power offers substantial opportunities for our energy future. One of the most significant benefits is its extremely low carbon footprint. As this chart shows, nuclear power produces far fewer greenhouse gas emissions than fossil fuels. Nuclear power plants create hundreds of permanent, high-skilled jobs, plus thousands of construction jobs, boosting local economies. Modern nuclear plants are designed with multiple safety features and have an excellent safety record compared to other energy sources. The future of nuclear power depends on balancing these challenges and opportunities. Innovation in reactor design, streamlined regulations, and public education are key to maximizing nuclear's potential. As countries work toward decarbonization goals, nuclear power could play a crucial role in providing clean, reliable baseload power to complement renewable energy sources.